So I want to start with a number today. $20.
Okay. That is roughly the price of a decent salad in San Francisco. Maybe.
Maybe. Or a cocktail if you're lucky. It is also apparently the cost to design a potentially viable drug for a new COVID variant.
Yeah. That puts the salad in perspective, doesn't it?
It really does. We are looking at a paper today that frankly feels like a turning point. It's called "The Virtual Lab of AI Agents Designs New SARS-CoV-2 Nanobodies."
It's from a team at Stanford and the Chan Zuckerberg Biohub, just accepted in July 2025.
And look, we talk about AI in science all the time, but it's usually AI as a tool, right? A scientist uses a model to help them think.
Right. It's like a super-powered calculator. You're still the one doing the math, essentially. You punch in the numbers, it gives you an answer.
This is different. This is AI as the scientist.
That's the key distinction, yeah. This is not a human asking ChatGPT for ideas. This is a human setting up a virtual lab,
Yeah.
stepping back and letting a team of AI agents run the show.
And they just run it.
They hire each other, they debate strategy, they write code, they critique that code, and then they output a molecule.
And they do it in a couple hours.
It's absolutely wild. And before we get too deep, we should mention this sits alongside other frameworks that are popping up, things like Target Pro and Target Bench.
Right.
There's this huge push right now to move from, let's call it artisanal discovery, handcrafting each experiment, to these automated, almost industrial-grade pipelines.
So the mission here was super specific. It wasn't cure cancer. It was target the KP.3 variant of COVID-19.
Which is a nasty target. KP3 is one of those variants that evolved specifically to dodge our existing antibodies.
So the challenge was, can a computer with almost zero human hand-holding update our biological defenses to catch up with the virus?
Exactly.
Okay, so let's strip this down. Because if I go to a standard chatbot right now and type, design me a nanobody for KP.3, it's just going to fail.
Oh, completely.
It'll hallucinate a protein sequence that looks like gibberish. Or give me a recipe for soup. Why did this work when a simple prompt fails?
It all comes down to the architecture. They didn't use one big brain. They use a multi-agent system.
Okay.
Think of it less like a chat with one bot and more like building a corporate org chart.
So who's on the payroll?
Well, you start with the human. The human's role is basically the admin. They just give the system the goal.
A high-level objective.
Right. The system then spins up a principal investigator agent, the PI. And the PI analyzes the task and decides who it needs to hire.
Wait, so the AI decides its own staffing?
It does. It looks at the prompt and says, okay, this is a biology problem, but it's also a coding problem and a prediction problem. So for this job, the PI hired 3 specialists.
Which were?
An immunologist for the biology strategy, a machine learning specialist to handle the predictive models, and a computational biologist to, glue the code and the biology together.
That's amazing. It's like Ocean's 11, but for science. And they're all Python scripts. But there was a 4th role, right? Reading the logs, this one seemed to be the real MVP.
Oh, the scientific critic is the secret sauce.
Okay.
You see, large language models, they kind of suffer from being people pleasers. They want to agree with you. If you ask, is this a good idea? They tend to say, yes, just to be helpful.
Which is fatal in science. You need someone to say, no, that's wrong.
Exactly. You need the peer reviewer from hell. And that's the critic. Its entire job is to poke holes. If the ML specialist writes a script, the critic reviews it. It doesn't write code itself.
It just demands better code.
Right. And in the logs, you see it catching these little logging errors, like, hey, you forgot to define that variable. Things that would have crashed the whole simulation. It's the safety rail that keeps the car on the road.
So you have this team. They have meetings, team meetings for strategy, individual meetings for execution. But they use this really clever technique to stop the AI from, getting stuck in a rut.
Parallel meetings. Yeah, this is a brilliant application of how these models actually work.
Explain that.
In AI, you have a setting called temperature. It basically controls creativity. High temperature is creative, random, maybe a little chaotic.
And low temperature is safe, predictable, but kind of boring.
Right, so if you want a new drug, you need creativity, but you can't have hallucinations.
So how do you get both?
Use parallel meetings. For a big decision, the PI would run the same meeting 5 times simultaneously, like in parallel universes.
Oh, I have different timelines.
Exactly.
Right.
And in these 5 timelines, the temperature is set to high. So in one meeting, the agents might argue for strategy A. In another, they get really excited about strategy B. They're just brainstorming wildly.
But then you have to bring it back to reality.
And that's the merge meeting. The PI gathers the transcripts from all 5 of those crazy meetings and holds one final session at low temperature. It looks at all the ideas, strips out the bad science, and synthesizes the best parts into one coherent plan.
It's like majority voting for creativity. That's incredibly smart.
It's crowdsourcing your own brain.
Okay, so the team is assembled. They're cloning themselves to brainstorm. Now, the actual strategy, they're going after KP by 3. And the agents had a debate about what to build.
They did. They weighed full antibodies versus nanobodies.
For anyone who hasn't been in a biology class recently, what's the difference there? Why nanobodies?
Nanobodies are basically just what they sound like. They're much, much smaller versions of antibodies. They come from animals like llamas and alpacas.
Okay.
And because they're smaller, they're more stable, they can get into tissues better. And crucially for this project, they're way easier to manufacture in a lab. The agents correctly figured out that for a rapid response, nanobodies were the way to go.
And then they had another choice. Start from scratch de novo design or modify something that already exists.
They chose modification, and the agent's reasoning here was very human. They basically said evolution is a great designer, so why ignore its work?
Right.
They found 4 existing nanobodies. Their names were Pi1, H11D4, and B21, and VHH72.
These are the old guard.
The old guard, exactly. They worked on the original Wuhan strain of COVID, but they completely failed against KPP3. The virus had changed its code, and the old keys didn't fit the new lock.
So the mission is upgrade the software, take these old soldiers, and teach them new tricks.
Precisely. And this gets us to the how. This part gets a little technical, but it's fascinating because the agents had to build their own toolbox. They picked a power trio of computational tools to do the job.
I saw this in the methods section. ESM, AlphaFold, and Rosetta. It felt very deliberate.
Oh, it's the holy trinity of computational biology right now.
Yeah.
Think of it like a funnel. First, they used ESM.
That's a protein language model.
Yep. It works just like ChatGPT, but instead of predicting the next word in a sentence, it predicts the next amino acid in a protein.
So it's basically a spell checker for biology.
That is a perfect analogy. It makes sure the new design looks natural. It filters out any Frankenstein monsters that would just, fall apart in the cell. If a mutation is statistically weird in the language of biology, ESM kills it.
Okay, so ESM makes sure it's readable. Step 2 was AlphaFold Multimer.
That's the architect, the structural expert. It predicts the 3D shape of the molecule.
Mm-hmm.
And in biology, shape is everything. It answers the question, does the key actually fit into the lock?
Mm-hmm.
If the nanobody just bumps into the virus instead of latching on, it's completely useless.
And finally, Rosetta.
Rosetta is the physicist. AlphaFold tells you if it fits. Rosetta tells you how tight the grip is. It calculates the binding energy using physics simulations.
And the agents actually came up with their own scoring formula to weigh these 3 things against each other.
They did.
I have the formula right here. It's a weighted score. WS equals 0.2 times ESM plus 0.5 times AlphaFold minus 0.3 times Rosetta. That negative on Rosetta threw me for a second.
Yeah, that's just a physics convention. In thermodynamics, lower energy is better. It means a more stable, tighter bond. Think of a ball rolling down into a valley. It wants to be at the bottom. A very negative energy score is actually a very good thing.
So by subtracting it, a more negative number becomes a bigger positive for the total score.
Exactly. The AI gets thermodynamics. But look at the weights they chose. They gave AlphaFold the highest weight, 0.5.
Half the score is just the shape.
Because if the shape is wrong, nothing else matters. Structure is king. If the key is bent, it doesn't matter how hard you try to turn it.
So they run this loop, they mutate the old nanobody, they check the spelling with ESM, check the shape with AlphaFold, check the grip with Rosetta, and they just rinse and repeat.
4 full rounds of directed evolution. And remember, the human researcher is just watching this on a screen.
Yeah.
The agents are writing the Python scripts to chain these tools together, debugging their own code, and parsing the results.
And after all that, they spit out a list, 92 candidates.
92 DNA sequences. But this is the reality check, right? You can simulate a sandwich, but you can't eat it.
Right.
A virtual lab is worthless if the biology isn't real.
Right.
So they had to go from bits to atoms. They actually synthesized these 92 designs in E. coli bacteria.
This is the moment of truth. Because usually when you design proteins on a computer, they fail in the real world.
That's the sim-to-real gap.
Yeah.
The first test was just expression. Did the bacteria even make the protein, or did it just turn into useless goop?
Or did the bacteria just die?
Exactly.
Yeah.
But here, 38% produced really high yields. Only about 6% failed completely. That's a very, very high hit rate for computer-generated designs. It proves the ESM spell checker worked. These were stable, valid proteins.
Okay, so they exist, but do they actually bind to the virus?
They do. In fact, 85% of the new designs had better structural confidence scores than the originals. But we have to talk about the two hero molecules, the ones that actually solved the puzzle.
The winners. Let's hear it.
Okay, so the first was a mutant of Tai1. The original Tai1 was totally blind to the JN.1 variant, a close cousin of KP.3. It just bounced right off. The AI version, it gained the ability to see it. It learned a new target.
That's impressive. It expanded its range.
But the second one, this NB21 mutant, that was the real star. The AI swapped out 4 specific amino acids. I mean, the names are technical, I77V, L59E, and so on. But the result was a nanobody that kept working on the old virus and gained the ability to neutralize the new KP.3 variant.
So it didn't just trade one for the other, it became a universal key.
It successfully updated the biological weapon,
Well,
and it did it by navigating this incredibly complex landscape of being both a stable protein and a sticky protein. It's a balance a human just can't calculate in their head.
however, I want to play the critic here for a second. It wasn't perfect. There was a messy situation with a cysteine mutation that caught my eye.
Ah, yes, the H11D4 mutant. This is a great example of where the AI still falls short. On one of the designs, the AI introduced a cysteine amino acid.
And why is that a problem?
Well, if you're a protein chemist, you know that cysteines are like molecular Velcro. They love to form bonds with other cysteines. So if you put a lone cysteine on the surface of a protein...
It makes the proteins stick to each other instead of to the virus.
Exactly. It resulted in what they call high nonspecific binding. The protein just clumped up. A human structural biologist would have seen that sequence and immediately flagged it. Don't put a cysteine there. The AI missed it.
So they lack that deep, intuitive, almost common sense that a human expert builds over decades.
For now, yes. Which brings us back to the human element. The paper says the human researcher only wrote about 1.3% of the text in the whole interaction.
But that 1.3% is the steering wheel.
It is. The AI is the engine, but it doesn't know where to go without that initial prompt. It didn't know which variant to target or which tools to use until the human set the constraints. And obviously humans had to do all the wet lab work.
We're not at the point where the AI just 3D prints the drug on your desk.
Not yet.
But let's talk about the economics. We started with the price tag, $20.
That's the token cost for GPT-4o to run all the meetings, write all the code, do all the reasoning, between 10 and 20 bucks.
And the time.
A few days for the entire design phase. Compare that to a human team. You'd need an immunologist, a structural biologist, and someone who can code in Rosetta and Python.
Finding one person with all those skills is a unicorn. Hiring a team takes months.
And massive grants. The virtual lab spins up that expertise instantly.
Yeah.
It basically democratizes the heavy lifting of science.
It connects right back to that Target Pro idea we mentioned at the start. We're moving toward automated discovery. If I'm a grad student with a laptop and 20 bucks, I suddenly have a research team that rivals a pharma company's department from 10 years ago.
That is the really exciting part.
Yeah.
It suggests a future where the bottleneck isn't having a good idea or even designing the experiment. The bottleneck becomes strictly physical. Can you synthesize and test things fast enough?
So here's the thought I want to leave you with. If one virtual lab can design a working drug candidate in an afternoon for the price of a pizza, what happens when the next pandemic hits and we spin up 10,000 of them at once?
It changes the entire game.
Are we ready for science at that speed?
We better be, because the viruses certainly aren't waiting for us.
A fascinating future to think about. Thanks for diving deep with us today.
Always a pleasure.